So the next presentation is on low power. Again, something which a lot of people mention now as we get to more complex SOCs of tough power budgets. A lot of people are quoting low power verification as one of their challenges. So this is a paper from Francois Cerisier, who's the manager of TVS in Grenoble.
Okay, thanks for the introduction. So I'm Francois Cerisier. So as Max mentioned, we're working on customers' projects in Grenoble. So this is actually coming from a customer project we are working on in France. So we had this kind of design which actually integrates an existing IP from a third provider. But because there are lots of pressure to get the power consumption down and down and even lower, they actually decided to cut the IP in pieces and to provide different means to manage the power at different block levels inside the IP. So they actually inserted this IP into a larger subsystem, which includes also PLLs, DLLs, sensors, and so on, and lots of control registers to deal with the power consumptions. So the IP is actually a multimedia IP doing graphic processing. So just to give you some background. So if you look at the characteristic of the powers, then I'm not going to talk too much about the functional aspects of the design, but much more on the power. If you look at the power, the design has been cut in different power domains, the main one being the subsystem, which is almost always on, so it's off when the system on chip decides it to be off. Then you've got all the control registers, which are, again, almost always on, but they are a bit more on. You need to access to them as soon as your IP is available. And then you've got the IP itself, which is doing its own processing in general, but some blocks, so here the block B, is not needed all of the time. Unfortunately, it's also a block which consumes lots of power, so they need to switch off or to reduce the power of this block depending on the applications. In terms of complexity, so the design has been cut and put in different hierarchical power design. There are other SoC switch domains that are involved. We've also got inside the design 12 different power domains which have 6 different possible voltages. So if you look at that, you end up with a quite huge number of possibilities to test if you really want to be exhaustive. We also need to test when they are off or when they are in underdetermined states. So the complexity is really exponential, and somehow there is no way you're going to test all of this. About the power techniques which are involved in this design, so the basic one, so one actually which is not in this slide and which is used and which has been used for years is the clock gating. But then you can also decide to switch a power domain off completely, which actually requires you to insert isolation cells so that your IP, your block which is off, doesn't corrupt data on the buses or on the control interface. Another technique is actually to reduce the voltage of the power domain, but then you cannot run at the same speed, so there are also restrictions to the rest. You also have technical issues if you're too low in voltage. And another one, which is a bit more complicated to put in place, is the dynamic voltage and frequency scaling, so DVFS. So it's typically saying if I need full power, the full processing power, I higher the voltage, which allows me to increase the frequency and I run fast. In the other way, if I need my function but not so much, I lower the frequency, I lower the voltage, and consume less power. So these are the techniques which are involved in the design and that we needed to verify. So our goals were first to verify the RTL. So the RTL has some features. We need to verify the functional correctness of the design. But most of the work has been spent in the low power verification. So we needed to verify that we conform to the power specification. We needed also to verify that in the different power modes, the design was still behaving properly. It's not because you switch off one block that the rest of the design cannot work. The rest of the design should work. So in terms of verification techniques, so the RTL, this is, everyone is used to verify RTL using simulations or formal techniques. The power intent is coded in UPF, so it's part of the design. The UPF is really part of the design. It's the power intent which is coded in UPF, and that's need to be tested. It contains the power domains, it contains isolations, level shifters, power states, power transitions. There are lots of stuff you could do in the UPF. So we have static checks that are provided by some tools, which are more structural checks. We have then the ability to run power-aware simulations, which takes both the RTL and the UPF, and then you run you simulate your design with more information than just 0 and 1, which is what you do in RTL. So for the static checks, this is the kind of thing that the tools provide. So you can check structural checks for under multi-voltage, consistency, architectural checks. There are also some structural functional checks, like for the isolations and power switches, which are done by the tool automatically. In terms then of simulations on use cases that test that you really need to run then. So the first thing is to verify the low power state machine. So we need to verify that the state machine is actually able to reach the different states, the different power states we are targeted. We need to be sure that the state machine, depending on the operation mode, is actually going to put the design in a lower power mode. So this is mainly doing traditional testing, test development, exercising the registers of your design, the functional part of your design. But then we need to check that there is no violation, and we need to check that we end up in the right power state in the end. Checking the power states, so it's actually kind of an issue, because the designers, the architects may want to see some states which are valid. So these yellow cross here are the states that are being specified as valid. The issue is that when you move from one state to another one, so you change the power supply of two different, the voltage of two different power supplies here. When you move from one to another one, you actually end up in states, power states which are not defined, which are not specified. So the tool reports errors because it's not specified, but in the other hand, it's just transition states. And you don't really care about what's going on there. But you still need to be sure that once you're in the final state, your design still behaves properly. So then, what we had to verify on top of checking that we ended up in the right poor states, we also needed to be sure that the design was behaving properly. So for instance, if we got such architecture and if we switch off the block B here, which is doing some processing but not all of the time, when we switch it off, then we need to be sure that the interactions that he usually has with the other blocks doesn't corrupt the other blocks. So we need to run functional tests, which are exercising the other blocks surrounding the block B here. So we developed tests actually to switch off this kind of blocks and make sure that there was some use cases running on the block A here. So again, in verification, the main issue is to say when we are done. So it's probably dictated by the management and the planning. But nevertheless, you still need to describe what you're going to verify, what needs to be verified to get some kind of confidence. So we've developed the verification plan to describe the important transitions, the important poor states we wanted to reach, and in which modes we wanted to run functional tests. So then from this verification plan, so we had coverage metrics and so on, a number of tests, blah, blah. Another thing that we could also look at is the coverage database of the poor state table. Unfortunately, this table has got 2,000 million possible states in it, so we would need at least this number of tests. And this is kind of impossible. So we really need to be able to cover only the interested conditions, the corner cases of this, all of these tests. So some thought about this. So actually, there are lots of states in the poor state table. We could do much more automation to reach more of them, probably not all of them. We could also think about a way to filter what we target versus all of the states. So we're not interested by the 2,000 million states, but probably by a few hundreds. Another thing is there is little support today in the different tools for assertions, which are crossing the Verilog VHDL domain and then goes to the UPF. So we have very little means to see, okay, I've got a functional event, I've got a functional sequence. Now I should check that the poor state domain, the poor supply is in this voltage. So there are today little support on this from the tools. Also, as I mentioned, there are different there are intermediate states which are not valid, which are only transitional states. We don't really care of them, except that in the end, the design should be correct. So the tools should probably provide better support of this. So as a conclusion, I mean, UPF is an extension of the RTL. It should be seen as part of the design. As such, it should be verified. So we need means to verify the poor intent of your design. There is, I mean, some people say things that are not verified don't work. It's probably true for most of the things. It's probably true also for the UPF. The UPF, although it's poor intent, have some impacts on the functional side. If you're not able to switch on a block, then your design is not going to work. So this should be carefully be taken in consideration. EDA tools, are evolving every day on this. It's probably where they put some efforts now. But there's still room for improvement to automate testing of this, and also, as I mentioned, crossing the boundary between RTL and UPF. Okay, any question?
You just have to repeat the question. Okay.
Yes, in one of the slides, we said that the low qualification most of the time that functional verification. Was this the functional verification? Was it only a limited scope, or it really that was so much more complex?
Yeah. So the question is because the poor verification was taking much more time than the functional verification. What was the scope of the functional verification versus the poor verification? So the IP came from a third provider, and most of the functional aspect of this IP has been verified previously. So the functional verification we did was mainly running integration tests on this IP and being sure that the state machine and all the controls which are in the register side were okay.
There's a question from Mike.
Simple question. You stated there's a tremendous amount of power states, but actually the big problems are the power transitions. Did you manage to identify the really interesting states, and how many transitions of them?
So there's no easy answer to that. So we've got, there are a few millions power states which could describe. So if you look at transitions, it's even more. So you could multiply by 1 million, and it's probably still not true. There's many ways you could go from one state to another one. So we haven't identified this, all of this. What we've done is that we have identified interesting states we wanted to reach and on which we wanted to run functional tests. So we identified all the corners, basically, so where the interesting parts. In terms of transitions, we had to decide a few of them. We couldn't verify them very much. In the end, if you find a transition which works, you always say to your management, yeah, there is a way to get this IP working.
There's just one question from the web, which is basically, what sort of percentage of the states are interested?
It's actually a very small percentage. We've identified something like 50 or 50, 60 very, very important combinations that really needed to be verified. Then doing more, I mean, if we were able to do 500 more random in between, that would be better.
Okay.